discuss and stimulate discussions on one of the most disruptive technology shifts of the decade.
Ladies and gentlemen, we are so honored to inform all of you that today we have Dr. Sibake Udgata, Professor at the University of Hyderabad, Dr. Manas Ranjan Patra, HOD and Professor at Berhampur University, and Dr. S. Krishna Kumar, STO at DRDO, Chennai, amongst us.
I'd now like to take the honor to talk about Dr. Sibake Udgata. He is currently serving as a professor in the School of Computer and Information Sciences, University of Hyderabad, India. He also served as the Director of Center for Modeling, Simulation and Design, University of Hyderabad. He has done his PhD in Computer Science in the area of mobile computing and wireless communication. His research focus is on intelligent algorithm for wireless communication and related domains, and published more than 100 research papers. He is currently working as a principal investigator in many Government of India funded research projects, mainly for development of wireless sensor networks and applications of swarm intelligent techniques in cognitive radio network. He is a recipient of IBM SUR Shared University Research Award for the project Mobile Sensor Network-Based Disaster Management System with emphasis on rescue management.
Let me now take the privilege of welcoming Dr. Sibake Udgata to give keynote address.
Good morning. I know it's a challenge actually, early morning. So, but anyway, I promise you that I will not bore you. And okay, so thanks to the organizers, particularly Madam Padmalaya, for inviting us. It's not about inviting or not about coming here and other things. We also feel that what we do in last almost a decade, so we'll try to summarize the work what we did almost in a decade. And it's not only my work, there are many people who have contributed to this, and it's not proper to claim that everything I have done it. And so many people, like people from electronics, people from biology, so people from other departments also have contributed, and of course so many students. So I thought I will put up a slide, then there are more names and it doesn't make any sense. So the title of the talk for another 40 minutes or so, I will be talking about intelligent sensors and what are the various issues there and what we have done for that. This diagram has nothing to do with that. I don't work on neuro kind of a thing. It's an image which I borrowed from Google Image, and just to tell that there is something intelligence going on in the sensor network, right? So, yeah. This slide is just there to pick up the tempo. If somebody comes late also, you will not miss anything, right? So, so this is a Wikipedia definition. I mean, I don't have any, I have not added any word or any comma or any full stop there. So, it's exactly Wikipedia definition. So, what we say that even if you have a sensor, so the sensors at some point of time we need this discussion, but right now everybody knows that, so I can skip it. But only point I want to highlight here is that if you look at the last slide, a sensor sensitivity indicates how much the sensor's output changes when the measured quantity changes. So that's the last line. So I want to just talk about the last line here. A sensor sensitivity indicates how much the sensor output changes when the measured, when the measured quantity changes. What I want to highlight is that the change is not linear. So there is a change, definitely there is a change, but the change is not linear. What I mean by this is, suppose the temperature changes from 25 degree to 30 degree centigrade. Let's say the voltage changes by 5 millivolt. When it changes from 30 to 35 volt, the voltage may not change by 5 millivolt, it may change by 7 millivolt. So the change in the output is not directly proportional or directly linearly proportional to the change in the input. And that's a challenge actually. So the challenge is that when the input changes, the output changes, but the change is not linear. The change is non-linear. So that's one of the challenge here. This is again courtesy Google image. It's an image of various sensors. So the sensors comes in different sizes, different forms, different capabilities, different outputs, different type of outputs. So everything is possible here. A sensor is as small as a dust and is as big as a room. So it's almost like that. So this picture tells us what are the different types of sensors available, and just to have a feeling about the different types, size, form, capability and all these things. And of course cost also. It starts with 10 rupees to 10 lakh or 10 crores of rupees. Okay. This is, I picked up this image from some Facebook image, not exactly related to this, but I just wanted to tell you that it has a much of a relevance within smart and intelligent people. If you look at this, nothing to do with racism or nothing to do with boys and girls, but just an image, right? So if you look at, read this one. The difference between a smart man and a wise man is that the smart man knows what to say and the wise man knows whether to say it or not. So it is used in some other context, but let us use it in the sensor. We have used it in the sensor network concept also. The idea is that every sensor will observe data, right? Measure the data. Now once you measure the data need to be sent to the server or the sink. Now if you send the data to the server or the sink, then it's a normal sensor, right? It's a smart sensor. It picks up the data, it measures in a very smart way, and then collects the data, puts it into an IP packet, and then sends it to the server. That's the first thing. Now the second thing is that whether I should send the data or not, that the intelligent sensor does. Because sending the data is more power consuming, more energy requirement is there, instead of observing the data or computing the data. So for example, I can tell you one small example. If I have to send a data for a distance of 1 meter, let's say the power requirement is P1. Now if I have to send the data for a distance of 2 meter, the power requirement becomes 10 P1. So it almost increases by 10 times if the distance doubles. So the distance is an important factor actually. So if you want to communicate and the distance is too far, not even too far, if you little far also, then you tend to consume a lot of power. And the power consumption is almost 10 times when the distance doubles. That's one. And the computation power and communication power, if you compare, 90% of the power is consumed by the communication and only 10% is consumed by the computation. So the idea behind it that if I can reduce the communication and then if I can conserve the power, then the sensor network will live for a longer time. So in this case, when I talk about intelligent sensor, one of the intelligence or one of the component is that the sensor knows whether I should send the data or not send the data. Now let me give you an example what we did here. Again, courtesy one of my PhD student. For example, let's say in the morning the temperature is morning 6 o'clock, the temperature observed is let's say 28 degrees centigrade. In summer at morning 6 o'clock the temperature is 28 degrees centigrade. Anybody will say that it will be around 35 degrees centigrade during noon time. So there is a change in temperature that it changes from 28 degree to 35 degree when the time changes from 6 o'clock in the morning to 12 o'clock in the afternoon. Now this we know. Now suppose you develop a mathematical model and run this model in the sensor and they run this model in the sink or the server. Now what the sensor does, sensor runs this model, estimates what should be the value at this point of time given the past record, and let's say the temperature becomes T days. The server also runs the same model and estimate that the temperature is T days. Now what is the advantage with the sensor here? The sensor also measures the temperature. If there is not much of a difference between T days and the measured temperature, the sensor knows that the server also knows that there is no need to send it. Now, if you imagine also, say for example, if I get salary on 28th of the month, or let's say 25th of the month, I know that I'm almost 90% of my salary is consumed, and I don't have to ask anybody for loan and because I still have 10% of the money. That's a process every month. So I have this model. For some reason, if in 1 month I spend the money, then I need money from some friend or so. So what is that we are trying to do is that we have developed a model. The model will be there in the sensor. The model will be there in the sink. The model predicts the output. The sensor measures the output. If there is not much of a difference between the predicted output and the measured output, because the sensor also knows that the sink is also doing the same thing, you don't need to send it. The sink will only create a record there. Now this experiment we did with University of Berkeley, California. They have a Intel lab. They have almost 2.5 million records of data they have collected in the Intel lab. And those 2.5 million records were usually sent to the server. Now once we run this model, we achieved up to 91% saving. 91% in the sense that we predicted what will be the next output, and we measured the sensor output, whatever is available there, and we found that they are almost matching, so we don't need to send them. So that's the purpose of this slide, that you need to know whether you need to send it or not. And I thought that this is the right way of saying this, a smart man knows what to say and the wise man knows whether you want to say it or not. And that's true with any real life situation also. Now if you look at a sensor system, I go back to a little bit of electronics, not much. It's a normal standard conventional sensor. You have an input signal, you have a sensor there, you have some output signal. The output signal is analog. Analog means it is measured in terms of voltage or current, and then you have a measuring instrument display. You take any digital thermometer, right? You put it there, you get your data. So it measures in terms of analog signal. The analog signal is converted to display. That's a standard sensor. Now look at a little bit of smart sensor. What do you do here? Same thing up to this point. So you have an input signal. The sensor gives me a voltage or current. ADC stands for analog to digital converter. So it converts to the digital, and there is a small microcontroller, whether it is ARM or any microcontroller. Then either you display directly or send that communication, right? So that's a smart sensor. So the smart sensor, what it does, it collects the data, converts to the digital format, either displays it or sends it, communicates it. Look at intelligent sensor. The intelligent sensor says that you take the input signal, there is a sensor here, it gives me voltage or current, then there is an analog to digital converter. The digital data comes to the microprocessor, and here it is. There is some intelligent algorithm which is sitting in the microprocessor itself, and the whole thing is a sensor node, right? The whole thing is a sensor node. There is a microprocessor, there is an analog to digital converter, there is a sensor, and there is the input signal, whether it is temperature or pressure or humidity or whatever it is. So the input signal comes, the sensor converts it to a voltage, then the analog to digital converter converts it to the digital data. The microprocessor plus the intelligent algorithm here decides whether it to display or communicate or to take some decision. Now who gives the intelligence? From where this intelligence comes actually? All these things. So I don't want to take away any credit from anybody else. The entire computer science branch is here. So if you look at who gives the intelligence here, this intelligent algorithm comes from, you take statistical signal processing, you take conventional artificial neural network or fuzzy logic or genetic algorithm, particle swarm optimizer, whatever, blah, blah, blah. All these intelligent algorithms, depending on the suitability, depending on the requirement, you can choose one and these things. One I added here, this is deep learning. Because these days people say that if your slide doesn't contain deep learning, probably you are not a fresh actually. So I just added a deep learning here, but it's as good as a neural network, it's as good as a multi-layer neural network and all these things. So deep learning is again, why I said this, the deep learning, what is that company? TI, Texas Instruments. Texas Instruments have come out with a chip. This microprocessor is already there, and then this intelligent algorithm in form of deep learning is already embedded into it. So that chip is already there. So I thought the intelligence comes from these things actually. So the design is same. We have an input signal, then this ADC, then microcontroller PC with intelligent algorithms for the signal processing. You put it here, okay, and then the display is there. Okay. Now the nature of sensor data, we have to talk a little about that, then we slowly move on to that. So the nature of sensor data is that first if you look at a sensor, one sensor may take 1 second to observe the data, and another sensor may take 10 seconds to observe the data. For example, mean, I have to tell this example because I have been working on this for quite some time, almost more than 5 to 6 years. If you take temperature sensor, it measures 10 observations per second. 10 observations per second, it can measure. But if you take I work on water quality sensors, etc. Suppose I have to measure the pH value of the water or the turbidity value of the water, it takes 10 seconds to observe one sample, right? So now you see, if I have a sensor board and I have multiple sensors, let's say 5 sensors are there, one sensor takes 1 second to read, another sensor takes 1/10 second to read, another second takes 10 seconds to read, another sensor takes 1 minute to read. How do you make it a complete TCP packet and then send it? One method is that you take the LCM of everything, wait for that time and then send it. But then if you have to wait, why a sensor? You buy a sensor or there is a sensor which gives you 10 observations per second because there is a requirement. So if you don't do that, then you are missing out some important information. So that was the challenge. So that was how many samples per second you are able to measure. So different sensors have different sampling rates. Bits per sample, how many bits you observe. Camera sensors are a different size, audio sensors are different size, acoustic sensors are of different size, temperature sensors are different size. So huge, the volume of data, for example, small, just temperature, it's a number. If you look at audio, it's slightly more. If you look at camera images, they are still more, right? So the size of observed data is also different. The number of times you observe the data is also different, and bandwidth requirement. So you have to store it and all these things, communicate it. So all these things are important. Now whether you like it or not, the world is full of sensors. If you want to avoid sensors, probably it is not possible. I mean, even if you close your doors and all these things, still sensors are there. Everywhere sensors are there. And if no sensors are available everywhere, we have enough sensors in our body, right? So, I mean, if somebody asked me, I mean, I remember one talk was given by that Kharagpur IIT professor Sudeep Misra. He asked in the audience, how many sensors are there in this room? So people started looking at their mobiles and all these things. Every mobile is around 3 to 4 sensors or 5 sensors. So around 100 people were there, so they say around 500 sensors are in this room. Then he said it's almost close to infinite, countable infinite actually. Every human cell is a sensor. So you have so many sensors actually. So your cell phones are sensors, your surveillance cameras are sensors. Arvind Kejriwal is coming up with an idea of putting surveillance camera throughout the Delhi. So they are all sensors actually. Your GPS receivers are sensors, your motion sensor, light sensor. So whether you like it or not, there are sensors everywhere, right? So what is the plan is that if you connect all these sensors, then it becomes a sensor network. And the medium of communication is, if it is wireless, then it becomes wireless sensor network. And if you connect this wireless sensor network to internet, then it becomes Internet of Things. That's the protocol actually. The protocol is that I have sensors, I connect them through a wireless medium, they become wireless sensor network. And if this wireless sensor network is connected to an internet, then it becomes an Internet of Things. Now the problem with connecting to the internet is much more complex than just forming a network. Because internet means it should be accessible from anywhere in the world. Now you know the problem with one of the things is that you can collect data, right? I mean, at one point of time, I don't have that slide here because that's not required. There will be approximately 50 billion devices will be connected to the internet by 2020. That's what the McKinsey people predicted. Now, 20 billion devices, if they are connected to the internet by end of 2020, 50 billion means we are around 4-5 billion people, right, in the world. So everybody will have 10 sensors almost per head. Now, if that is the data that will be collected, where to store them? Storing, okay, we have storage. Then how to index them, how to retrieve them. Now also I have so many pictures in my desktop, in my laptop. But if I have to search that, let me find out my photos of Manali trip, I have to search for half an hour, where is it? Because you have not indexed it, you have not properly put it in that format. So if you have data of collecting data coming from 50 billion sensors and they are stored somewhere, how to retrieve them, how to store them, how to index them, that itself is a challenge. Second more important challenge is that this portability, right? We measure temperature in degree centigrade. Some other country measures temperature in degree Fahrenheit. Some other, there are different formats. Different formats of the data is available. Different formats of the sensor output is available. How do you bring it to an open data format? So people who are working on ontology and all that, they are working on this open data format. The format has to be open and everybody should be using a particular format, standard format. They are not there. So I record the temperature in degree centigrade, somebody records the temperature in degree Fahrenheit, everything is there in the internet. How do you collect them, how do you take decisions and all that. So all these things comes under this intelligent algorithm thing and you have to look at all those things. Now, problems, and that's where we start actually. The problem is manifold. One problem is that the sensor accuracy increases only with the cost. For example, if I want to measure temperature of order only integer, 25 degree or 26 degree or 27 degree centigrade, if in that order, then probably it cost you only 100 rupees or less than 150 rupees. But suppose I want to measure temperature to the accurate up to 1 decimal place, 25.1, 25.2, suddenly it becomes 500 rupees. If you want temperature sensor to measure accurate up to second decimal places, 25.11, 25.12, 25.13, it becomes 5,000 rupees. If you want to measure temperature between 20 degree to 40 degree centigrade, 100 rupees. If you want to measure up to 100 degree centigrade, suddenly it becomes 500 rupees. 1000 degree centigrade, it becomes 1 lakh rupees. So the accuracy comes, but accuracy comes with a huge cost. So if you are happy with a mediocre sensor, that's good. You don't have to worry too much about it because the cost is very less. But if you want a high quality, high precision sensor with a wider operating range, the cost is almost in terms of lakhs. So and it increases exponentially. That's one challenge. The second challenge is that because the sensors are cheap, very less cost, they are not very reliable. They are not very accurate. They are not very reliable. They are not tested properly. So if you bring a lot of sensors, form a network, you find that 20% of the sensors are not working. Now then what happens? So you should have a model of redundancy, repetition, right? I need to have a sensor network where I assume that 20% of the network will fail at any point of time. That's the assumption. Whereas that assumption is not true for a normal network. The normal network doesn't assume that my network will fail, my system will fail, my node will fail. In the sensor network, my basic assumption is that this node will fail. 20% of the time this node will fail. So the node will fail with a probability of 0.2. So the fault tolerance is also an important issue here. Third probability that can you use them? I mean, can I take a sensor which is low cost? Can I use a sensor which is not that reliable, not tested properly? Use algorithms, intelligent algorithms, etc., and make it more reliable, make it more fault tolerant, make it more operating range. What is operating range? Operating range is that suppose I take a sensor and it says that you can measure only between this point to this point. This is the range. But can I do some algorithm which will extend the range beyond this and beyond this? For example, if you buy a sensor, the range is normally the range is, suppose you take body temperature, right? Thermometer is only between 95 degree Fahrenheit to 105 degree Fahrenheit, only 10 degree Fahrenheit. Now that doesn't work everywhere, right? For environmental temperature it doesn't work. And for a blast furnace I cannot use the same temperature. Now the challenge here is that can I take a low cost, low reliable sensor, use algorithms so that the reliability increases, with the same cost I can increase the operating frequency, operating range. So what is the operating range? If the manufacturer says that it will work between 20 to 40 degrees centigrade, with algorithm can I make it 0 to 60 degrees centigrade or 0 to 100 degrees centigrade. So I'm using the same old sensor, but I'm using algorithms to see that the sensor operating range can be extended. That's one model. So that's an intelligent sensor. And main problem is, as I started saying, non-linear. Non-linear in the sense, now I give you an example actually. Again, I go back to the water quality sensor. There is a sensor called pH. pH is a sensor which says that it measures between 0 to 14. The range is between 0 to 14. 7 is neutral, 0 to 7 is acidic, and more than 7 is alkaline. Now that's a standard thing, right? You take any water, measure the pH value of that. The pH value says that if it is 0 to 7, it is alkaline, sorry, it is acidic. Between 7 to 14, it is alkaline. 7 is neutral. The World Health Organization says that you can drink water, it's a potable, if the value of pH is between 6.5 to 8.5, right? If the value is between 6.5 to 8.5, it is safe, you can drink the water. Beyond that, you should not drink the water. Now the problem is pH is highly dependent on temperature. pH is highly dependent on salinity. pH is highly dependent on the oxygen content of the water. What does it mean? It means that you take a glass of water, measure the pH value, let's say it is 7, completely neutral. Apply heat. Now when the temperature changes from 25 degree to 35 degree centigrade, the pH value changes from 7 to 6.5 or 6.4. That means what? It is dependent on temperature. Not only temperature, it depends on salinity, oxygen and so many other things, gas and all that. So what I mean, the conclusion is that the same measurement, the pH sensor will give me one value, and that value is not in conformity with the other environmental factors. They don't take all these things account. So what does it mean? It means that I take a glass of water, measure it, let's say it is 8, then I apply heat, that it becomes 9. So that doesn't mean that I can drink the water which is 25 degrees centigrade and I cannot drink the same water which is 35 degrees centigrade. It is the same water. But unfortunately the algorithms are not there to compensate it. So the sensor doesn't have the algorithm to compensate it. If temperature is 35 degrees, if the value of pH is 9 at temperature 35 degrees centigrade, what should have been the value of temperature, the pH value at 25 degrees centigrade? So I have to come down to the normal environment and measure, find out that value and then decide whether I should drink it or not drink it. Now that is also easy if it is a single thing. Suppose it is only temperature and it's only pH, you draw a characteristic curve and write a small algorithm. But unfortunately, it is not only the temperature. There are many other factors, number one, and these factors are also interdependent. Temperature change, dissolved oxygen changes pH, pH changes dissolved oxygen changes salinity, salinity changes dissolved oxygen. It's a very complex formula. It's not a formula, it's a very complex dependency. And again, one more complex, I'm adding one more complexity here. The value that changes with temperature is not consistent. With 1 degree range in the temperature, this much value will be changing in the pH value, in the sensor value. That's also not there. There's a nonlinearity. So, and the nonlinearity, you know, any nonlinear problem is a difficult problem. That is one. The second problem is, I said multi-parameter compensation. Multiple parameters are there and you have to compensate it. And third problem is the drift. What is drift? I give you an example. You go to any shop, right? You buy potato or dal or rice or whatever. There is a weighing machine. It's nothing but a pressure sensor. If it puts there, then there is a pressure there and based on that pressure, it gives a value. Now mostly what you see that you go to that weighing machine, it gives some value, 5 or 10 or something that it presses one button. What is that button? To neutralize it. So it makes 0. So that means I am giving a bias of -5. If it is 5, I give a bias of -5. So that now if you measure, if it is 105, then it shows 100. Now the problem is this. The problem is that you take any pressure sensor, apply 100 gram weight, right? It gives 105. So you give a -5 bias so that it becomes 100. Now give 200 gram weight, it becomes 207, not 205. You give 300 gram weight, it becomes 310, not 305. You give 400 gram weight, it becomes 420. You give 1000 gram weight, it becomes 1050. So what does it mean? It means that the drift what you have, the drift changes with the pressure value. The drift changes with the pressure value, number one. Number two, the drift change is also not linear. It's not constant. Now, if you are buying potato or rice or something, it is okay. I don't mind 2 grams or 1 gram. But if you are buying gold, you can't afford it, right? So if I have a pressure sensor, that's what exactly I am telling. If I have a pressure sensor, if I am weighing it, and I say that the bias is 5, that means everything that is weighted, you have to subtract -5. That is not going to give you correct result if your range of measurement is different. Now, what you have to do, we are still living with it. I'm still living with it because I don't mind paying 2 grams extra or 3 grams extra because I'm buying atta, aloo, piyaz or something like that. So that is okay. But if you actually want some experiments where diamond, gold, etc. need to be measured, it has to be accurate up to 0.00001. And that 0.001 accuracy is not there. So these are the basic problems with sensors. These are the basic problems with sensors and these are the basic problems with the electronics behind the sensor. You can't help it. Now what we can help it is that can I think of some algorithms which will help us to compensate these things and try to find out a much better result compared to what the actual sensor is giving. So what is that I am trying to do? I am trying the sensor output, I am trying other inputs and I know that the sensor has these problems, designing some algorithms so that the sensor output becomes more acceptable. That's the whole idea of this talk. Now if you look at this nonlinearity compensation, right? I think I said that there is nothing much in this slide. The only thing is that the cheap sensors gives nonlinear output functions. The output function is a nonlinear function and I understand and assume that everybody knows what is a nonlinear function. The nonlinear function is that the change in the x-axis, the change in the y-axis, you don't get a straight line. You got a complex line there. It's a nonlinear line. So, and the nonlinear compensation is not a x square or x cube or x4, etc. It's not a parabola or it's not a circle or it's not a order. So the complexity is more there and that complexity needs to be modeled and it is not there. The complex conversion of large size lookup table. What do? People come out with say that forget it. You take some measurements and then create a table and that table will give you, look at the table and take the value. But what happens to the table, you cannot draw, design a table for 0.001, 0.002, 0.003, or even if you 0.001, 0.0001, 0.0002, that also is not possible. If you want to do that, then the table size becomes very huge, and you don't have enough memory in the sensor to put all the table size there. So that's one problem. Unfortunately, we can't have an ideal sensor, and then the problem is that is it possible to linearize the output hidden to the user? So what is that we are trying to do is that we are trying to make the output linear. The user will not be knowing it, but the sensor will run this algorithm, convert the output to a linear output, and then give you back the result. Okay. So nonlinear sensor, nonlinearity in sensors, I think I explained in all possible manners. So many electronic devices, instruments and sensors exhibit inherent nonlinear input-output characteristics. That is a fact, and you have to live with it. The second, before I go further, what do? You take a sensor, measure the readings, and plot it. Plot it means plot x-axis the observation, y-axis the observation, x-axis the input. You find a nonlinear curve there. What these vendors, companies do is that in any nonlinearity curve there is an area which is linear. Suppose you draw a pattern like this, right? So there will be one area where it looks like linear. So they take only that one and say this is my operating range. I hope you understand. So if I plot it, suppose the graph becomes like this. So here it is linear. In this part it is linear. I only say that this sensor will work only in this operating range, because beyond that it is nonlinear. Within that it is linear. What we propose is that okay, forget about this. Can I convert the entire nonlinear graph to a linear graph so that the operating range can be extended? That's the idea actually. So in this case, there is an inherent nonlinear characteristics. The vendors or the manufacturers, what they do, they say that they look at the characteristics curve, find out in that characteristics curve which part is linear, and they say that my sensor works only in this range. Beyond this range, it is your risk. We don't want to come in here. So that operating range we need to change. Nonlinearity also creeps in due to change in the environmental condition. I gave you an example. Temperature changes, pressure changes, oxygen changes, gas changes. So when the environmental condition changes, we also have a nonlinear condition there, because they are dependent on that. They are not independent. Aging of the sensors also introduce nonlinearity. Aging of the sensor in the sense, the sensor which you buy today, you take thermometer sensor. If it becomes 5-year-old, the doctor says that it is no more working, you throw it. The aging, because aging resistors, capacitors, etc., whatever there in the electronic components are there in the sensor, they start aging. And when they start aging, they don't function the way they should function. So there is a drift there also, and that drift also can be compensated. You can put age of the sensor as an input to the system, and then if this is the age, what should be the original value actually. So that also can be done. So effect of nonlinearity, they said that there is a problem with the range, there is a problem with the accuracy of the measurement, and the characteristics are usually time varying and unpredictable. You cannot predict the characteristics over a period of time, over a period of different environmental conditions, etc. So these things are a problem. I don't want to talk about neural, because we have used neural networks, etc. So just I want to say that we have used neural networks, and neural networks are what then? There are some input layers, there are some output layers, there are some hidden layers, and then you start learning actually. And I don't want to go beyond that. So the nonlinearity compensation, what we have done is that there are two ways of doing it. One is called direct modeling, and the other one is called indirect modeling. It's not very difficult actually. When I go through the slides, you can make it out. And what is direct modeling? Look at this. It's a very simple model. Let's say we have a system here, and we have some inputs. Xi is the input, x1, x2, x3, x4, they are the inputs. Now the system gives me a function value, fi. So the system is what? There is a neural network. You give this as an input, the neural network gives me some output. I repeat what I said. I said that the system consists of a neural network. I give the input here, the input gives me some output. Okay, I accept it. Then this is the sensor output. Then the same input I train it to the neural network, right? Then I get some output. Then what I do, I try to find out the error here, and based on that error, I change the neural network. I repeat what I said. I said that I have a system with sensors and all these things. I give my inputs. The sensor system gives me some output. That's the actual output. The second output is the neural network output. So I repeat again, what I said is that there are some inputs. The input can be temperature input, gas, carbon dioxide input, oxygen input, whatever. Then there is a system which consists of the sensors, which gives me the values. Now these values are fi, function of this I. and then I give the same input to a neural network model, the neural network will also give me an output. Then there will be some error. Now this error I use it to train the neural network. Why I am doing all these things? I am doing all these things that once the neural network is trained, the system can be removed. We don't need a system there actually, because the system output is trained for the neural network. So what I do, I remove this part and give this input to the neural network only, and I get the output. So this model actually, these days we call it as a soft sensor. What is a soft sensor? We don't need a hardware sensor actually. You give me some inputs about the different other parameters, I can predict the fifth parameter. Suppose you give me parameter 1, parameter 2, parameter 3, parameter 4. Fifth parameter is also a sensor is available, but if it's dependent on these 4 parameters, I can develop a model. Input 1, input 2, input 3, input 4. The output is the input 5. The output is the input 5. If I can do that, then input 5, for input 5 the sensor is not required. I hope I make sense. What I am trying to say is that there are 5 sensors. The fifth sensor is a output is also dependent on the 4 sensor outputs. And the 4 sensor output, it's not a linear output, it's not linear. So what I do, I give this 4 sensor output to a neural network and predict the fifth sensor output. And the prediction will be wrong at the first stage, but with multiple iterations, I will try to predict that the fifth sensor output is the exact output of the 4 inputs here. After this, I remove this fifth sensor and replace it with this software. So what happens, this becomes a soft sensor. This becomes a soft sensor. The soft sensor in the sense that I replace a hardware sensor with a soft sensor in a particular range, etc. So direct modeling is an example of a soft.
But in that case, I think you are not sensing the real time.
No, I am not sensing the real time. What we did is, initially, when we set up the network, we use the fifth sensor. Initially we use the fifth sensor to do it, to model it. Once the modeling is done, remove the fifth sensor and replace the software. So there what happens, I don't have an actual sensor there. So that's an intelligent sensor, or that's a soft sensor. The soft sensor replaces the hardware sensor. Now we know the advantage of soft sensor actually. It doesn't cost, it doesn't do anything. So you can do a lot of things with that. I can repeat it without any cost. I can just copy and paste it at different places. So this is what is direct modeling. The
Because of the neural environment, the timing parameters and the testing parameters, they just impose the erroneous topics, and we say we want to replace a model directly with this.
Anyway, I don't want to go to the neural network, but let me tell you what is a neural network here. The neural network has a capability of error compensation, error neutralization, all these things are there. But what you said is that it requires proper parameter tuning, proper choice of learning algorithm, proper choice of what type of neural network you want to use it. I say that all these things are suppose known. Now if all these things are known, I can use a neural network box and then train it. And once the training is done, how to train it is itself is a research, how to train it. Now if I can train it properly, and I say that there are experts who will help me in training it, once I train it, I don't need that fifth sensor. That's what the point is. Now if I cannot train it, so there are multiple cases here. Suppose there are cases where I cannot train it. Now if I cannot train it, I have no option to use a hardware sensor. But there are cases, almost in more than 50 to 60% cases, where a hardware sensor can be modeled by software. And where it cannot be modeled, we accept it. We will use the hardware. Anyway, hardware sensor is there. So this is called direct modeling.
So in that case, we don't have issue of aging of sensors.
We don't have issue of aging of sensor. We can take all these things into software itself.
Aging of the sensor is the inherent property of the sensor itself.
Aging of the
No sensor can give the correct value infinitely.
No, that's what I'm saying. Aging of the sensor is the inherent characteristics of the hardware sensor. Aging of the sensor is not coming into software sensor. That's what his point is. So inverse modeling, this is another interesting thing. What is inverse modeling? You take any input, set of inputs, xi, then your system gives a function. Now if you look at the previous slide, this function and the neural network that we are doing. Inverse modeling is that I take any input, use a system, the system gives you function. The system consisting of sensors and all these things, hardware sensors. Your inverse model, we have an inverse model here. No, it's like this. I give you temperature, it gives me pressure. Now I give you pressure, it gives you back the temperature. That's what is the inverse modeling actually. So x will predict y, and if y is given, what is the x? So that is what is the inverse modeling. So inverse modeling is that I give one input, it will predict the other one. But if I have the other input, what it should predict the other one. So that is called inverse modeling. So if you look at this, if I give this input, the system gives me a model, and then this inverse model is there, the same model actually, that gives me one output. Now this output is compared with the input itself, right? So this input gives me a sensor output. The sensor output is inversely modeled to give me again the previous model, and this one is compared with the original input. Now if this I can again train it, then you know that given the output I can predict the input. So that's also one way of doing things, and this is all part of the software which will be there embedded into the sensor. Now if you look at this diagram, what is that we are trying to do, and you see what is that we are trying to do. This blue line is the actual sensor characteristics. That means if the voltage increases, this side you have the pressure, and actually the sensor is like this. The output is like this. So it's a simple example to tell you that there is a nonlinearity. So this, and what this sensor manufacturer says that look at this area to this area. It almost looks like a linear line, right? So they say that it works between 0.4 to 0.7. They don't say anything because below this it's slightly difficult to predict. What we do is we predict this green line. This green line is actually the inverse function of the blue line. Now if I superimpose this green line with the blue line, it's an inverse of that, right? Then you get a linear line. Now this linear line, it starts from 0 to 1, right? It operates in, of course this is normalized plot actually. So because I have normalized it 0 to 1, any range, 0 to 100 or 0 to 200, etc. So what happens now, this nonlinearity is now compensated with this nonlinearity. You get a linear curve, and now I say that instead of measuring only between this range, you measure the whole range. Now question comes that whether for all sensors we can do it. At least for some sensors we can do it. Some sensors we have done it also. For some sensors I can do it. For some sensors I may not be able to do it. What is the experimental parameter here? The experimental parameter here is that I take the sensor. Even if the sensor manufacturer says that you operate it only between 25 to 50 degrees centigrade, I operate it between 0 to 100 degrees centigrade, plot the characteristics curve, find out the inverse of that, and then multiply it, store it in the sensor itself. Now I say that my sensor can measure between 0 to 100 degrees centigrade with the same old sensor which I purchased with the manufacturer specified parameter that 25 to 50 degrees centigrade. So I could extend the operating range which the sensor would have costed a fortune with a software, with an algorithm. So the same model here, I give the sensor output, that is the VT, there is a neural network, and this gives me some output, the temperature goes back here and correct it. So this is basically I am trying to compensate it or making, we call it the linearization of the nonlinear characteristics, right? I mean that's a typical course subject in any computer science or any mathematical courses, etc. Now if you look at this, this is a nonlinear, this graph is about nonlinear drift compensation. The nonlinear drift from any drift is what? With 0 input you should get 0 output, but unfortunately it is not true. With temperature, with input 0, your output should be 0. For example, if your weighing machine, there is no input, the output should be 0. But unfortunately, it is not 0. It is showing some 5 or 10 or 15 or something. They press a button to neutralize it. But I am only saying, arguing that neutralization is not enough, because that neutralization minus 5 or minus 10 is not uniform, constant across the operating range. So that we want to change it. So if you look at this, now look at this blue line again. The blue line again is a nonlinear drift actually. It goes like this, again it changes like this, etc. Now what we want, again we want to change the drift. The drift is that if it is 5, I need to know that up to 100 grams, the change is 5 grams. But after 100 grams, the change becomes 7 grams. After 200 grams, the change becomes 10 grams. After 300 grams, the change becomes 17 grams. So this nonlinearity, again we have used this green one. And then this drift, now you see that this is the line. The red one is the line. So that means whatever is the drift in the sense with aging or with other conditions, the drift will be there, and the drift is nonlinear across the measuring range, and we need to compensate it. So this compensation, again you have used a neural network, so that these inputs are given to them, the output is compensated. So what is that we have done? We have done a simple algorithm for reducing the number of data that is going to be sent. We have done an algorithm which will extend the operating range with accuracy. We have done an algorithm to compensate the drift in the sense with aging or without aging. So these 3 algorithms we try to put it inside the sensor itself, and thanks to my colleagues in electronics, etc. So they put it in the sensors. Now that sensor which we purchased at 300 rupees is equivalent to a sensor which is almost equivalent to 3 lakh rupees. That's the idea.
Here one point is whether you go for software or whether you go for hardware. The sensor part is always hardware.
Yes.
That cannot be substituted with any software.
Yes. Yes.
So those parameters also should be considered if you want to cost factor.
That's what I'm saying. I take the same sensor. I'm knowing that the sensor is not that reliable, the sensor gives me some error, etc. I give you an example actually. I have another 10 minutes time. Anybody? Okay. So I give you an example actually. There in this slide. I will come back to that. I don't want to take time now. So I know that the sensor is a problem. I know that the observation is erroneous, and I know that how the error comes in. And what we have done is that in that microprocessor, that intelligent algorithm part is there, that plus intelligent algorithm, I put this algorithm there. And that algorithm takes the input, does everything there, and the output that comes out is more reliable, more accurate compared to the original output. So I am not replacing the hardware sensor, I am making slightly intelligent.
And in the other part is we should also have to know the value with the aging factor.
Yes, yes.
So
How
that data should be available.
manufacturing date? Manufacturing date is always available to me.
Yeah, of course. That will be available.
So the current date is known. That's the processor knows. The manufacturing date is given as an input.
But the thing is, manufacturing, even if you purchase something and you don't use for a long time and then we start using, the aging concept
Varies a bit, of course, varies a bit. So you, of course, all these things are there. What you have done is that it's not that you have tested it for 5 years. So what you have done is that you have assumed certain things, right? You have assumed certain things, gave us an input, and then try to find out that whether it is working or not working. But as you rightly said that this has to be done over a period of time in the field. Over a period of time in the field, because the same sensor, if I do it in Hyderabad, the same model may not work in Jammu Kashmir. Because Jammu Kashmir, the environment is different, temperature is different, altitude is different, everything is different. So the same training should be done there. But the model remains same. The model need to be changed. Model need to be trained again and replace that algorithm or replace those parameters in the same sensor. So that's not a big deal. What we have done is that it's an initial idea, and then we try to do it. Okay. So and I told that this is all the theoretical part of it. Then how we used it actually. So we have been intelligent algorithm for interdependency compensation of environmental parameters. What we did, we took a DO sensor. DO means dissolved oxygen. How much oxygen is present in the water? There is a sensor, and the sensor cost almost 40,000 rupees. And unfortunately, although it is 40,000 rupees, it doesn't give correct result. In fact, when we started working on this model, we thought we'll buy sensors, connect them, and do some communication, and our job is over. That was in 2008 when we started this work. Now slowly we realized that what we thought and what we are getting is quite far. And now in 2018 I realized that we are at least 10% done. Initially in 2008, after 6 months we thought we were 90% done. Slowly we realized that we are only 10% done until 2018. Because there are so many problems, and if I have to depend on accurate result, reliable result, etc., it's far from accuracy. So what happens? DO is measuring how much oxygen is present inside the water. That is required for so many applications, right? Now, how much oxygen is present, that is dependent on pH, that is dependent on temperature, that is dependent on salinity, and there is a nonlinear dependency. So what we did, we purchased that sensor, created that characteristics curve and all these things, and tried to see that can we find out the actual DO value given all these constant parameters, and so that it becomes little bit more accurate, little bit more reliable. So that was the idea actually. So the proposed a model for dissolved oxygen sensor compensation based on artificial neural network. And this is, we have temperature, salinity, dissolved oxygen. These three parameters we used are used as input parameter, and normalized dissolved oxygen is the output parameter. So we give this, so whatever dissolved oxygen sensor gives me, whatever the salinity the sensor gives me, whatever the temperature the sensor gives, there are also other parameters, we have considered only three. We give this parameter the input to the neural network, and we find out what is the normal dissolved oxygen if all these things are constant, what should have been that is the output. So we trained it and we found it, all these things. And we use different statistical techniques and all these things. These are all neural network techniques and all that. And if you look at this, in the first case we are not very successful. As somebody said that artificial neural network itself is erroneous. So it requires a lot of tuning, lot of parameter available, etc. So if you look at this, there are the measured ones are blue line, and the ANN model gives me the red line. So initially we are not able to tune it properly. If you look at this ANN model result for 2020 multi-layer perceptron structure, it didn't work properly. Then we changed the algorithm, etc. Look at the below figure. You don't see almost any blue line there. So it's almost I'm able to, in the upper line you see that there is a blue, there is a green, red and all these things. That means there is a difference. I could not model it properly. But when you come down to the below figure, you see that there is almost a similar structure, right? We don't have much difference. We could exactly predict what should have been without these values. So similarly, this I want to come back to that. We have a, what do you call it, depth sensor. Ultrasonic sensors are there. You give an ultrasonic sensor, the wave goes, the wave goes, and then it hits an object and then comes back. You measure the time of flight. Everybody knows that what is the speed of the ultrasonic wave, 331 meters per second. That's the standard thing. But let me tell you, 331 per second, what we assume to be the speed of the ultrasonic wave, varies from 280 to 480, depending on the different environmental conditions. Depending on the different environmental conditions, it can vary from 280 to 480. What we assume is 331 meter per second. Now, I tell you what is the problem. The problem is that we experimented it actually. We took a overhead tank, and the overhead tank it's almost 2 meters, and then you put a sensor there. The ultrasonic wave speed depends heavily on humidity and temperature. There are other dependence factors also, carbon dioxide, oxygen, etc. So humidity, temperature and other factors. We considered only humidity and temperature. If you consider only humidity and temperature, look at this actually. So if your temperature is 5 degree, relative humidity is on this side. The table says that 8.27, 0.91. This is the percentage change. So this is almost 20% variation. So if you look at this, the total percentage increase in the speed of sound, ultrasonic sound, from 0 degree centigrade with the different relative. So the total percentage 0.91, 331 multiplied by 0.9, this side. Now if you change the temperature up to 40 degree centigrade, humidity becomes 100 degree centigrade, it changes by 8.27. So that's the difference range. So what is my problem here? My problem here that if you put it here, and because there is a humidity and there is a temperature variance here, the data that comes, the time of flight I measure with 531 meter per second. Now we have in a 2 meter tank, we have almost 40 cm. Water is available, but my data says that there is no water. At 40 centimeter means almost 20%. 20% water is always there. I mean, you don't get full tank actually. 20% water is there and my data says that there is no water. The tank is already full. My data says that it is still 20% empty and it is overflowing. So the problem is that, why the problem? Because when the water comes in this area actually there is a lot of humidity and there is a lot of temperature because they are outside. And this with temperature, the speed varies almost 20%. If the speed varies 20% and you take 531 meter per second multiplied by time of flight and other things and measure it, and that measurement is not correct. Now this is also, if you look at this, they are not actually linear. Again, they are non-linear. So what we did is that again this is the graph actually, how the value, the speed changes with the different temperature and different sample. What we did, same model, we took temperature, we took humidity, we took and another problem. Even if I measure a temperature and humidity here, I measured a temperature sensor here, humidity sensor here. So what is that it is measuring? It is measuring the temperature at this point, measuring the temperature, humidity at this point. But the humidity has a gradient here. Nearer to the water body, the humidity is high, and here the humidity is less. So I cannot have a series of humidity sensors actually. My humidity sensor is here, water body is here, and the humidity gradient is there between this humidity sensor and the water body, which I am not able to measure. So what we did, same model. We used a neural network technique, used this values, we found out what is the exact measurement and what is the value that comes out from the sensor. Trained it. Now with almost 400 cm, up to 400 cm, 400 cm means 4 meters. Up to 400 cms, earlier I am getting almost 360 cms, 40 cm of the error. Now I am getting 399.2. So that's the difference that we are able to do it only with, and you say that there are some papers, earlier paper also, where they say that they take temperature, they take humidity and compensate it. But we took an intelligent algorithm because the humidity value here, the temperature value here is not consistent across this entire range, the time of flight. So it actually changes. So the wave actually doesn't go in a straight line because the change in the humidity, it becomes a curve. And if it becomes a curve, it also comes back as a curve, and that also needs to be compensated. And the curve has a more distance than the straight line, right? And that we need to compensate. So this is what we did. So this is also, we had a different level monitor. We found out what was the exact value, what is the change in the value. We found that there are a lot of changes actually, and this is one such graph. We exactly use, I was given another 5 minutes only. I mean this graph is enough actually, and then I will put. We tried all these things actually. So for example, you take, again same thing, I've been working on water quality. So we took some 5 input parameters, pH, turbidity, DO, ORP, oxidation reduction potential, and then salinity, etc. So 5 or 6 parameters. And these 5-6 parameters are interdependent, as I told you, they depend on each other. There are a lot of other temperature is also there. There are a lot of other factors. So what we did is, I mean, this is simple work. We took all these things and you see these are the measurements. We convert, and there is a water quality index, weighted index actually, W1 multiplied by this, W2 multiplied by this. And there are different water quality indexes. For example, NSF has one index, Australian has one index, Canadian has another index, Indians have another index. So many indexes are possible, so many standards are possible. So what we did, we took the inputs, found out all the indexes, right? All 5-6 indexes, whatever there. And then we converted them to a single line. This is the single line. So this single line is the threshold value. And this value converted to a single value, suppose somewhere the value is more than this line, more than the threshold value, we call it an alarming event. Now alarming event, what we did, NSF has one alarming event. So for example, it says that for NSF standard it becomes alarming, for Australian standard it's not alarming. We didn't say, we say that in any standard if it's alarming, let me tag it and put it as a separate basket, right? I put it in a separate basket. These values are alarming. And in addition to that, we also took an user feedback. For example, this quality is a perception, right? You can't model quality as a quantity actually. The quality perception changes with the time, because I remember when I was used to travel by train actually, every station I get down, fill my bottle and drink it. That was 20 years back. Now even if I buy a bottle also, I see which company it is, right? So, and now if you give me a glass of water, I will drink it here. Probably an European professor will not do it unless he opens in his own hand. So that's the quality perception. Quality perception changes with people, changes with place, changes with application, changes with time. And this thing had need to be modeled. So what we did is we modeled this and said that the user feedback is also there. So I have my all data. There is a training model, and the training model now gives me a different standard, which is combination of all these 5-6 standards. So what we did, we found out all these things, and then wherever there is a alarming event, I put it separately. Then I used a clustering technique. Everybody knows that clustering technique. So some clustering techniques, then they are clustered. Now after they are clustered, if I get an alarming event, I try to see which cluster it belongs to. Now for example, the one cluster says that this is an alarming event which is natural. Over a period of time it happened because there is a small change. There is another cluster which says that if you add something, immediately there will be some changes, right? That's another type of cluster. There is a cluster where there is only one parameter changes. There is a cluster where multiple parameter changes. So we have different type of clusters. Now that gives me an impression that if my alarming event goes to this cluster, probably there is a intentional contamination. If my alarming event goes to this cluster, probably there is a natural contamination. If my cluster goes to this parameter, probably there is a multiple contamination. If it goes to this cluster, then probably there is a single contamination. This is also intelligence. We put that algorithm and found out this. So what we did is basically we tried to find out that all these things taken together, we found some theory behind it, found some application behind it, and then of course wrote some couple of papers on behind it actually. So this is a project actually which funded us for quite some time, from 2008 to 2017. Of course it's still running, and I don't want to. I mean, these are some of the deployments and where you deploy it, how do you get it. So these are Google Maps and all that, forget it. There are some students and all that. Okay. I just want to take 2 minutes because I thought I will talk about this and it's very close to my heart. What are the research issues actually? How do you do it actually? It's not that we are born researchers actually. Everybody can do research, even Einstein did like that. So first thing is that you have to find out what is the problem that excites you. If it doesn't excite you, probably don't work on it because you don't go anywhere actually. This forced research doesn't work. Now domain of the problem. Once you know the domain of problem, can you model the problem? Because that's very important actually, right? If you cannot model the problem, if you are not trained enough, if you are not good enough to model the problem in a mathematical form and all these things, you find some other problem. Now here you find a suitable problem actually. The third problem is what people have done about this, and that is very important. If you feel that you go to Google actually, there are so many people, so many groups have done a lot of work on that actually. So if I say what people have done about this, you have to read a lot. And believe me, without reading, there is no shortcut solution. You have to read a lot. After you read a lot, question the formulation. It's not about only reading. You have to question why these people have done like this. And you know, I was in Thailand for some time, in Bangkok, and the Thai people asked me that, you know, Indians are doing much better research than Thailand. You know why? I said, why? I don't know. He said that you have a habit of questioning. And we people are ruled by the king. We don't question, we obey. So if you obey research, then you cannot do different research unless you question. So questioning is important actually. And when you are reading, you have to question it. And when you question it, question the formulation, question the experiments, question the results, start questioning actually. They are not perfect. For example, whatever I have done it and I am not perfect, you have to question me. And if you question me, you are not questioning me directly. That question will give you some answer, and that answer is a new paper actually. So, and then what are the gaps or assumptions made? That's very important actually. Any paper makes some assumptions, and that assumptions are made, let me tell you honestly, those assumptions are made because without those assumptions I am not able to solve the problem. For example, I have made some assumptions here. The assumption here I have made is that I have not considered the height of the experiment, altitude. That's an assumption. I have not considered the gaseous state, oxygen, carbon dioxide, etc. We are not considered. That's an assumption because I don't have those sensors. I didn't go to Jammu Kashmir to do this, or I didn't go to Everest to do this. So those assumptions need to be considered, how they have written it, or they have inherently written it, or they may not have written it also. But you have to find out. For example, in mobile computing, when I was doing research, people will experiment it with mobility 5 meter per second, 6 meter per second, 7 meter per second. And conveniently they will avoid more than 10 meter per second because that is not working. The algorithm is not working. So you have to see that what is that they are not doing. What are the assumptions they have made in all these things. So what are the gaps and assumptions made? This gives you the scope for the future work, and maybe the technology was not available at that point of time. One question is that they say people are not fools actually. If I am doing a lot of work here in intelligence sensor, when I am presenting here, there is another work that is already going on. If I have left that, that means the technology, I have achieved a particular saturation level, and at this point of time I am not able to do much about it because the technology is not available. For example, this Ola, Uber, all these things were not there because GPS was not that standardized. Now that the GPS was standardized, people are coming out with solutions. So you have to see that because the technology has evolved, now there is a possibility in that. So do you have expertise, for example, in any college or in any university or any institute, do you have the expertise to solve this problem? Do I have the necessary tools? Do I have the necessary experiments? Do I have the necessary hardware for doing this? If not, forget it and move ahead. So start working for a solution and pray for a bit of luck. Research also requires a bit of luck actually. I mean, you can't solve all the problems. If somewhere the luck has to favor you actually. So pray for a bit of luck, but all these things, bit of luck comes only at the 10th step. All 9 steps you have to do it, and finally you pray for a bit of luck. What we did is, I mean, in fact, all these things are quite clear. There are 4 types of research we do. We have existing problems, existing methodologies. And you can write a paper with that, take that problem, try 4 methodologies. One has to be good because if you have 4 methodologies, one has to be good. That's one way of doing things. The second problem is, there is a problem, but over a period of time a new methodology has come, swarm intelligence has come, deep learning network has come. So can I take the existing problem and I use a new methodology? That's a little better research. New problem, existing methodology. Problem is new. New problem has come out with it was not there. But when the problem comes, I can use the existing methodology and do it. The 4th one is new problem and new methodology. And the difficulty level increases with the order. 1, 2, 3, 4 in the same order, the difficulty level increases. But I must tell you that one may not be able to start at level 4. You don't have to aim at level 4 only, not level 1, 2, 3. I will only do level 4. That will not happen. You have to work 1, 2, 3 to get to level 4. I mean, there is no direct shortcut path actually. Okay. So that's it. I want to stop here actually. The only thing is that don't miss the opportunities. If you get a chance, if you get a problem, if you get an idea, work on it. And if you don't work, for example, while you are working on existing problem or this 1 or 2, you may get an idea about new problem and new methodology, which actually people don't get. If you get that one, don't miss the opportunity and work on it, however time it takes. Thank you very much. Thank you for your time.
Thank you, sir, for giving us that valuable insight. Now I request our director, Dr. Jandyala Narayan Murthy Garu, to present the memento to Dr. Sibake Udgata Garu.
Thank you, sir. Well, getting on to our next honorable speaker, Professor Manas Ranjan Patra holds a PhD in computer science from the Central University of Hyderabad. He is a professor in the Department of Computer Science, Berhampur University. He was a United Nations Fellow at the International Institute of Software Technology, United Nations University, Macau. His research interests include artificial intelligence, cloud computing, data mining, and e-governance. He is a member of ACM and life member of CSI and IST. Currently, he has an additional responsibility as the director of the Human Resource Development Center of the university.
Let me now take the privilege of welcoming Dr. Manas Ranjan Patra to give the keynote address. Let me now take the privilege of welcoming Dr. Manas Ranjan Patra to give the keynote address.
Okay, that's okay. Sir, shall I? No, it's okay. I'll do that. I'll do that. So, a very good morning to all of you. First of all, I am thankful to be a part of this conference. I travel all the way from Odisha. In fact, I had some connection to this place because I studied from here, from Central University of Hyderabad. So it was nice coming back to the same place and delivering a talk in such a forum. In fact, most of my job has all been done by my previous speaker. And I was thinking that people, though they belong to a different place, working in a different area, they can think alike. But maybe, I mean, there are universal problems and many people just think on the same line. But I'll take a slightly different point of view. Basically, I'm trying to bring these three paradigms, a marriage of these three paradigms into applications in smart governance. So the topic is synergic integration of IoT, agent, and cloud computing paradigms. So that's what I'm going to speak on for some time. I know this is a time when I should be finishing, but I'll move a little fast so that we don't really create problem for the sessions that is going to happen after some time. Now, as you know that a lot of things has been already done in the name of e-governance, but I will not prefer to use the word e-governance, rather I will use effective governance or a smart governance. Now, if you try to define what exactly we mean by smart governance, it would mean something like this. It's basically a technology-mediated relationship between the citizens and their governments with respect to sharing of information, with respect to service delivery, with respect to timely response. And the overall idea is to improve the quality of life of the people. And if somebody expanded smart like this, simple, moral, accountable, responsive or responsible, and transparent governance. Now then, why I brought in this smart governance into a conference like this? And the moment you talk about smart governance, I think these are some of the very popular applications that come into our mind. We talk about smart cities, smart traffic management, smart healthcare, smart farming, and many such things. You have a big list and you can keep adding a few more smart applications into that. And in fact, there is no end to that. And people talk about connecting almost everything through the internet across the world so that you get the benefit of the things that you sense from all these IoT devices which are deployed in different application environment. This morning we heard about how they have been working on understanding the quality of water, whether this water is drinkable or not, things of that sort. Again, I will not go through the definition of what is IoT. I know that many of us are working on sensors, but I'll just bring your notice to IoT for me is basically a set of heterogeneous cyber physical objects which can be in the form of a sensor or actuators or an embedded system or a RFID tag or reader, even a small microprocessor which is deployed in a particular application. So anything that needs to be monitored, you can always think of as sensors. I think in the previous talk we saw a variety of, a plethora of sensors which are available to do anything. Now these objects are uniquely addressable so that you know from where you are sensing what. And they are deployed for a specific service, so you know the purpose. Something. Or maybe I have to just move a little bit distance. Yeah, that should be fine. Yeah. Now these objects can be deployed in different physical environment and for different cyber physical applications. But we were told that I think over a period of time, by 2020, there will be about 50 billion sensors which are deployed for different applications. That is what we learned in the morning. Now, what happens when you get so much of data? What you do with the data? So once we have so much of data that is available at our disposal, now the data scientists would say that yes, we have algorithms which you can use to do all kinds of analytics on the data. And probably these data are going to help us, help the government to deliver the service the manner they should, so that there is effective governance. So that is where probably the IoT devices can be of use to the government on different types of applications, and they can formulate policy on that. That could be one of the reasons. Now, what are we trying to achieve after all? So probably we're trying to achieve 4 different things. The first thing is we want to capture multidimensional data from different sources. So that gives us a multidimensional awareness of the environment in which you are working. The ability to gather information from different things which are deployed in different application areas, in different domains, in different environmental conditions. The ability to exchange information. Here I'm talking about machine-to-machine interactions. The ability to exchange information, that is machine-to-machine interaction. And the ability to process information intelligently. So this is what we are looking at to provide a kind of a smart governance for our governments. Now, what are the major issues? So as the number of things getting connected to the internet over a period of time is really increasing exponentially, and you heard about the number, about 50 billion by the end of 2020, even beyond that. Now there is an increase, there is a need for getting a large storage space where probably all this data can be stored. That's one aspect. The other aspect is there will be heavy traffic in the net where you try to push all our data into the network, because we become greedy when the data is available to us, and we want to make the best use of the data, probably not knowing whether all the data that we capture are really useful for our intelligent processing. I think we had a bit of that in the first lecture. Now, of course, the storage part will be taken care of. The storage part, now I think it's perfect. Probably the storage part can be taken care of by different cloud services that is available to us. And that's how people talk about sensor clouds and things like that. And I'm not going to deal too much about the cloud, because the cloud provider will provide all these facilities where we can push all our data to that. But the problem is with the sensing devices, which lack some kind of reasoning. Probably the sensing devices do not understand what they're capturing, and therefore they push all the data into the network and creating kind of a congestion and the requirement of heavy bandwidth. In a country like ours, when you still struggle to get our mobile devices connected, check our mobiles, and many times the network doesn't work, in such an environment you try to push all the data to the network, then probably you are creating problem. And therefore probably the sensors should be augmented with some kind of a intelligent decision-making ability, so that once they sense the data, they should know what is to be pushed to the network and what can be ignored. And even when we have all the data available in the cloud, you need some kind of a decision-making ability. We need some kind of a intelligent processing, so that you make the best use of the data that is available to you. So keeping these things in the mind, I thought one can think of a very high level architecture. Well, of course, in my talk, you won't find a lot of formula, a lot of experiments. Luckily, it's not there because already we are loaded with the stuff in the morning part. So before you go for the real presentation of the papers, so this is just a very high level architecture of an agent-based, cloud-supported IoT architecture, where I envisage there are 4 different layers. Down in the layer, we have the perception layer. You can also call it as a sensing layer, where you try to sense the data from varieties of devices, the things, double quotes, from where you want to sense the data. So that I call it the perception layer. And the previous speaker already has said that these sensing devices need to be smart, need to be intelligent. So they do a little bit of processing and they know what is the data they should put to the network layer so that you are not creating a congestion in the network. And the network layer runs different types of protocol to take the data from the network right to the cloud, which creates kind of a huge repository of data that can be used by the interesting people, those are interested in analyzing the data, the experts, those who like to analyze the data. And that is where I try to bring in the software agents as a layer which learns over a period of time the kind of data that they get and all kinds of prediction models, all kinds of different types of models that you build. Now, when the agents learn these models, even these models can also be kept in the cloud storage, which can be reused, which can be used by somebody else working on a similar type of problem. For example, in the University of Hyderabad, if they're working on understanding the quality of water, and a lot of work has been done on that, the same model can be probably placed in a cloud, and somebody else in a different part of the country can make use of the models to do the analytics. And then you have different types of applications, the application layer, where you run different types of analytics, data analytics, and different types of decision-making algorithms for the real use. And that is where I see the government, once these models are built by people working in the very low level with technical details, now those models can be used and can be further analyzed by different applications by the government to provide the right kind of service in different areas. Now, long back, I was working in this on software agents, on intelligent agents. I thought this very much matches with the kind of application that you are talking about these days. Now, what is an agent after all? It could be a hardware, it could be a software component, or it can be a combination of both, as we heard. That these soft algorithms can be put into the sensing devices, and that is how they exhibit an intelligent behavior. Now, the agents are such components which are deployed, which are situated in an environment, and they are capable of autonomous action in order to meet the design objectives, because you are not building sensors to respond to varieties of environment. So sensors are made for specific applications. That's how they have an objective to meet. Now, typically when you talk about software agents, software intelligent agents, it has certain attributes, it has certain characteristics, like the responsiveness, which means that the sense the changes that is taking place in the environment, and you respond to that depending on what kind of changes that is taking place. The autonomous behavior, which means that the agents have control over what they are trying to do. They have control over their own states. They have control over their own behavior. They are goal-driven because they have some specific applications in their mind, and therefore they are trying to achieve a particular goal. They're goal-driven. Continuity. They are working in an environment continuously. So they are continuously perceiving the environment for which they are designed. And the other one looks a little interesting, social ability. So here probably you can envisage is that the sensors are not working in isolation, but there is a constant interaction which is going on among the agents so that they exchange the data and they take collective decisions. They work together to solve different types of problems. Now, typically, it would look something like this. So inside the dotted line, that's where I have my agents, which perceives this environmental the factors to the sensors, and it creates a model of what it perceives from the environment. And there is agent functions which helps taking a decision, intelligent decisions. And if they're designed to act in a particular manner through the actuators, probably they will try to act on that. Now, what you would expect from the cloud, because we try to bring in even cloud into this kind of an architecture. Again, I'm not going to talk much about that, because I know that cloud provides a flexible, robust, powerful storage devices. So that is the aspect that you want to that you want to use in this particular context. They support scalable computation. They provide distributed real-time system management for an analysis of different IoT objects, and so on. So I'm not going to dwell too much on that, because the cloud provider knows what kind of services it's going to provide, either through platform, providing kind of a platform, the platform as a service kind of thing, or different software models, the software as a service kind of a model, or the infrastructure, the storage that you are really looking for, because there's a huge number of data, huge amount of data, huge volume of data that you want to store in my cloud storage. Now, what exactly you are trying to do is basically you try to augment the IoT by embedding this kind of intelligent softwares, not only in the sensors, but in the third layer, where you do higher level processing of the data, which is already filtered at the lowest level, at the perception layer, when the data was captured. Things should have an internal reasoning, so that's the reason why we need that the agents the sensor should have some kind of internal reasoning mechanism, so that can infer different things depending on the situation, depending on the scenario. And they should have the ability to reason about the environment, so that only useful information is extracted for further processing, so they don't capture anything and everything. And the intelligence of these things needs enough resources to run the software agent program. I think the cloud and other things will take care of that. Now, typically, the structure of a software agent would follow certain patterns. The internal dynamics of the agent looks something like this. So the environment states can be different. It's a set of different states. And there is a perception function which perceives things from the environment and creates an internal model. And the agent has an internal state which is updated over a period of time, because I said continuity is one of the characteristics of the agent. So as it perceives something new, an event happens, so that has to be captured, and it updates its internal state. Now, an agent has many actions, many options which are available. It can act in a particular manner depending on the scenario, depending on the internal state, and the things that is happening in the environment, the events which trigger different actions of the agent. So an agent should have a function to choose one of the actions for which it is designed. So we have a function called action. With the internal state, it can take certain actions. Now then, if the agent is also designed to take some kind of a responsive behavior, then there is a do function which takes the state into consideration, and the set of actions for which it is designed, and then it performs certain thing, and again the state changes because some action has been performed. Now, a simple high-level algorithm which really takes care of all these phenomena, that it starts with an initial internal state, and it continuously it works. So it gets the perception from the environment through different sensory devices, and we have different types of sensors for different types of applications. And when it captures certain things, it updates its internal state. And then, using this agent function, it can select certain actions which are appropriate in that situation, and it tries to execute those actions. Now, there are different models which has been proposed over a period of time. What should be the structure of an agent? But one of the structure which has a much acclaimed status in the literature is one that was proposed by Michael Bratzman. Of course, it's a very old concept. He says this is the way the human beings they reason. And in fact, when you look at the diagram, of course, I don't have the diagram here. It simply says that we have our sensory organs, and we capture things over a period of time, day in, day and night, and all that capture can be modeled in the form of some cognitive components like the belief, desire, intention. It looks like philosophical, but that's the way the agent states are modeled. Now, okay, I will not read the definition of that. So such agents which are driven by these components are known as the BDI agents, the belief, desire, and intention agents. And the agent takes input from the environment, and it builds the mental model using these three components. Now, for our simple understanding, the BDIs are nothing but the agent's information about the world. So when the sensor is deployed in a particular environment, the sensor knows what is designed for, what kind of information is going to capture, and what the job of that particular sensor is. Now, the desires are basically the agent's motivation or the possible options that is available to a particular agent, because the sensor will not be able to do anything and everything, but is designed for a particular option. So there are a set of options which are available to that. And what is intention for our understanding? It's an agent's commitment or the goals which are to be achieved in a given situation, and it becomes committed to achieve those goals. So that's the way the mental models are. And again, there is a high-level diagram which says that how the agents take the input from this environment through different sensing devices, different IoT devices, let's say, and interprets that, creates the belief base, which is basically a kind of a knowledge base on which the action will depend on. Then the agent has many options to do, and with all those options and the current inputs that it captures from the environment, it does the plan, and then that it becomes committed to achieve those goals, and then starts acting, and that's how it affects the environment change. Now, once again, one can define some high-level functions, and the real algorithms will go into each one of these functions. So the agent starts with some initial belief. So because when a sensing device is deployed, you know that what kind of environment. For example, if you have deployed a pH evaluator, a sensor which is going to read the pH values, it knows what it's supposed to do. Now, a belief revision function one can define, which will take the perception from the environment, and the belief of that particular agent changes over a period of time, is the belief revision function. Now, again, the agent has a set of options which are available to it, and an option generation function is needed where it will try to find what kind of desires which will be promoted, which will be upgraded to intentions or the immediate goals to be achieved. So there is a set of current intentions, and then there is a filtering function, because in a given situation, the agent is not going to perform the way it likes, but again, there is some kind of intelligence. The model will guide it so that there's filtering options, and then it becomes committed to achieve those actions. So an action selection function which finally decides, so this is the action that is going to be performed. So this is the internal mechanism which drives the agent to perform. So again, all those ideas are put in a high-level algorithm like this, which explains that how the agent perceives its environment, creates an internal model, and finds out its options, and in that particular situation, driven by a particular event, it becomes committed to certain options, and then it takes the appropriate action. So that's the internal mechanism. So I think this is again a high-level diagram, where probably I'm just trying to say that it's not just the action of a particular sensor or particular agent, but there is a collective behavior, there is an emergent behavior, or there's some kind of a social intelligence which emerges when the agents they interact among themselves. So that's kind of a scenario that one can envisage in a different situation. Now somebody will be asking questions, how do you write the agents? So the languages are available, platforms are available, frameworks are available. One can use any one of these depending on what kind of environment that you are working on. One can start writing those programs which provides to the primitives for communication, which provides the primitives to do the reasoning, and so on and so forth. So just to have a feel of what you can do. Now, since most of the things are already told, so all these models the architecture that I talked about can be applied in certain application areas where probably, okay, there can be many applications, but there are some of the applications which probably our country or any country would need, and that is where I just talked about the smart governance. Very recently we had problems in Kerala, for example, right? So water level monitoring, had the Kerala government would come to know that this is how there is a rising trend of water level, and probably the sensors deployed in strategic points, they would have raised an alert, and maybe some gates could have been closed so that it could have prevent this kind of things that is happening. I'm just keeping this slide for you to think without elaborating much, because already I've crossed my time. Now, load monitoring structures, if you go to the rural areas, for example, once the roads are constructed, after that nobody cares. Then they wait for some grants coming from some source, maybe from the World Bank, to again repair the roads. So there can be scenarios where you can deploy sensors which can find out what is the kind of load which the roads are taking, what is the kind of load which the bridges are taking, right? Now, those things can provide vital information for our government to go for preventive maintenance or even to plan how those roads or those bridges can be replaced because they have lived their life. Now, another interesting scenario, I think yesterday on a different context we are discussing with somebody else, independent living, because the number of aging people are growing very fast and there is nobody to really take care of them. So it's not happening only in our country, it's happening everywhere. I was just discussing that with Alexander yesterday during dinner time. So he was saying this is also the same story in Russia, in China, in other places. Then how we are going to take care of them? So we have wearable devices. I think there are many devices which can be really be of handy to such aging persons. And whenever you try to raise certain alerts, and there will be medical practitioners or volunteers, those who will try to make use of that data and provide timely support to these aging persons. Again, I'm not going to go through all that. It's just a picture to demonstrate. Now, people have also started talking about quantified things, quantified self. I want to monitor what is the status of my body. For example, yesterday again I met somebody, he said, I never suffered blood sugar, diabetes for all these years. Suddenly last time when I went to the drug checking and then say I had some sugar problem. Then I said, I have not tested for last 5 years. So you must check it. So these are situations where I want to know the status of my body. A person that can be equipped with different types of sensors. So n number of sensors are available. And those data can be sent to the cloud or to some certain other servers, where there are experts, those who can really analyze and predict what is going to happen to this person, what is the current status of a particular person. So quantified self. And there can also be a little bit of fun where people can talk about quantified bananas, quantified things, quantified fruits, where probably you're trying to predict how long it would take for the banana to spoil. Right? So if you have built a model in a particular place, the same model can be used elsewhere to predict how many days the banana would take to for a banana to spoil. So quantified bananas, so you can really keep track of that. So you have odor sensors, we have humidity sensors, we have temperature sensors. All sensors are now available. How to make use of that to have useful information on that. Now this is again smart healthcare. I think everybody knows that, how you can really monitor the patients. But this has some meaning in a rural, okay, I think it will come later. Now, there are also very interesting applications. I don't know, it would take some more time to realize in our country, where probably you're trying to monitor the accidents that are taking place. So there are sensors which are deployed at strategic locations, the road accident monitors. Once there is an accident, probably the cars, the vehicles, which carry certain sensors, we can send some data. So there are different scenarios, probably you can see. In the scenario one, then these two cars are moving and there is a collision here, and the signal is sent to some sensor here saying that yes, there is a collision, and immediately there are many other services which are activated. So the police is alerted, there are emergency ambulance services which are called, and maybe you are trying to warn the other drivers that there is an accident, so you take care of that, reroute yourself, things like that. Or maybe the insurance people are also called to have a inspection on that particular site, and probably you can think of many such things. So these are the applications which are of real use to the government to really act. Now there are challenges in the urban areas where one can really take help of these three different paradigms to be of some use to us. In urban areas we have problems of traffic, so you are looking for IoT devices to take care of that, to find out the parking slots and so on and so forth. So we also talk about smart buildings, where you try to adjust the lighting conditions, provide an ambient temperature based on the occupancy and so on and so forth. Solid waste is another very important application areas. I think many of the cities, they have started doing that. So where you try to locate where things have, when there is a pile of solid waste, and you take care of that. Water quality, I think in the morning, similarly the air quality, the pollution level and so on. Now these are some typical scenarios which are probably useful for the rural areas, where again through sensors you collect the data from the patients, and they are sent to different levels, maybe from the rural area from the primary health centers to the district hospitals, they have little specializations, maybe to some hospital up in the hierarchy, or maybe aims like things where in Delhi and other places where you need the intervention of real experts. So, so this kind of a scenario which can provide you continuous data from different sources, and there will be experts working in different levels, because you don't ask the experts to intervene in each and everything, but they intervene only when it is necessary. So that is how you can see the whole the hierarchy of the levels where the experts will be working, and they really help in kind of situation. Now, another applications, I think there are many people working on that, the IoT in agriculture. So a whole lot of things, smart farming, agriculture, drones, crop monitoring, smart greenhouses, and so on and so forth. So again, I'm not going to dwell much on that because I've crossed my limit. So these are some of the applications which are of direct benefit to the people living in the rural areas. So I mean, the list really goes on. And all the technology that you develop, if it can be of use to the common people, it's not just, we are not doing research just for fun, but maybe you're trying to help the government, and such input to the government matters a lot, because they just look for data. Now, if you have mechanism to capture the data and provide the right kind of model, provide the right kind of intelligence, how to handle the data, and you can really help the government to make smart. We can really make the government to be very effective. So that's the message they're trying to draw. So I tried my best to take care of the formula and algorithms and so on and so forth, because this is basically a very high level idea of how the sensors can be of use to us. It's not just sensors, but a marriage of these three different paradigms, these three different technologies, the IoT, the agent technology, and the cloud, because each one has its role to play. The cloud takes care of the volume of data that you need to store in days to come, in years to come. And the agents that provide you the intelligence that is necessary, either it's a machine learning algorithm or a typical sophisticated data analytics the program, or all that you have learned for analyzing the data, clustering, classification, and so on and so forth. So they are the driving machine, so they provide you the intelligence. And of course, the sensors are the devices which provide you, which are the source of data from different application areas. So thank you very much. I think I have kept myself within the time. And if you have questions, I think you should not have questions. Because, and if you can add, I'll be very happy if you can add one or two new applications that you can bring into this fold. That will be of use through these of the nation. Thank you very much. Sir, you had a question.
Sir, just an observation or a statement when I saw that interesting model, what you have said, beliefs, intentions, and desires. I was wondering, how come you do not have what is called idiosyncrasies? Idiosyncrasies. Because that agent can work at certain times in its own peculiar way, not following any other rules. So, which I call it as idiosyncrasies. I thought you should have even that part of it into the system. What I call is the departures or, aberrations or,
But I think, the computer scientists should be smart enough not to allow the agents to perform that way.
No, but because you have used the human mentality words there, sir, beliefs, intentions, desires, and one part of human quality is idiosyncrasies. Yeah. So I thought you should have that.
Okay.
Yeah. So
so in that case, I should not just have it, but I should have a mechanism to control that.
Yes, obviously, sir. Yeah. No, that's why I said, have you been sort of, maybe somebody has to work on that, so it completes all the human way of looking at things. So another one, when you have given all the attributes of the agents, like you have said socially responsible, autonomous, proactive, all that. I thought in that socially responsible you may have to add one more quality for the agent, that is, when it completes the job or when it dies in such a way it does not affect the environment. Your agent should be it should have that quality as well.
But I think in our scenario, such a thing never happens. The software will never die.
No, that agent need not be software. Na? That agent can be a hardware as well. Na?
Yeah, but the attributes that I discussed, keeping in mind that they are software.
Only software, this one, is it?
It's
not the actual sensor hardware part of it. Oh, okay. Okay, fine.
So the hardware people will take care of that raising of. This morning we heard about raising of sensors.
We want to expect linearity in our
Thank you, sir. That was definitely a value-added talk. Now I request our director, Sir Dr. Jandyala N. Murthy Garu, to present memento to Dr. Manas Ranjan Patra Garu. Ladies and gentlemen, now it's time for a tea break. Paper presentation sessions will commence after the tea break. For any further information, please get in touch with our help desk that is present outside. Thank you and have a good day. So the tea break will be exactly for 15 minutes and it will be followed by paper presentation sessions.